Okay, anything else for me? I want to get on to Carl.
So it's going to be intimidating right now in terms of the amount of stuff that you guys need to do. So there's a whole lot going on. So we talked about the UAUC airfoil coordinates. If you go through and just search for the airfoil coordinates database, you can find that. That's actually, that's not the correct link. It's this one. Right. So UAUC is University of Illinois at Urbana-Champaign. So Michael Seelig there's got a tremendous program there in terms of looking at different airfoils. There's a lot of wind tunnel data that's also available. They've done some of the propeller analysis. I included that in the typical ranges to look at the prop efficiency. Right. So there's a lot of useful information here, but this has many airfoils. So we can go through and look at some random ones. Let's say rotorcraft airfoil looks very goofy, probably not appropriate for our type of aircraft. But you see some of this low Reynolds number. It may be perfectly valid. Some of these have this low Reynolds number data. That means that there's wind tunnel data for that. You can go look it up. Right. So in this case, this is an 11% thick airfoil. And it's got a reasonable amount of camber. Kind of a thin trailing edge, but perfectly fine. If we look at the .dat file here, it doesn't look like anything, but this has those X, Z coordinates, and I can go through and save it, hopefully. In terms of so let's save this .dat file and we can go through and take a look at that. Hopefully this doesn't cause a problem. We'll look at it in Notepad. The typical format that's expected is the first line is just a name. And so whatever this is just a name. And so E214 is just the name of this airfoil. There's 2 rows of data. The first column here is the X coordinates. Right, so we're starting with everything being normalized with respect to the chord. So 1 is, that means that in the X, it's at the end. It's at the trailing edge, so it's at the tip of our airfoil. And the 0 means that it has a Z height of 0. Right, so these are normalized X over C and Z over C. We're starting from the trailing edge, going over the upper surface until we eventually get to a point that's very close to 0, 0. And then we go across the lower surface and we see now our Z values, some of them are negative. And then it finishes at the trailing edge again. So we start at the trailing edge, we end at the trailing edge. That's the typical format. So occasionally you will find an airfoil that is not in this format. Right? Sometimes they'll have the number of points in the second row and then it'll go maybe 1 to 0 and then 1 to 0 again, and you have to go through and reorder those. Right? If you need help with that, I can help you doing that. It's not difficult. You can open things up in Excel, go through, pull out the data that's in the wrong order, resort it, just a portion of it, resort it, and then save as a tab delimited text file, and it will still be readable with XFLR5 or XFoil or AVL that we're going to show. But that's the basic format that's being looked for. In terms of what airfoils make sense, that's something that you have to pick. And that's a very difficult thing to do. Some of these are labeled flying wings, for instance. Right? So this has a little bit of an up swing in the aft end of the airfoil because it's basically a self-balancing airfoil. Right? So we get a reduction in the pitching moment coefficient seen. And so this MH80, John talked about Martin Hepler. MH80 is an airfoil that we've used to build flying wings before, and it has a little bit of that twist there. And it's a very thick airfoil. One of the parameters that we care about in selecting the airfoil is the thickness to chord ratio. If you have a higher thickness to chord, everything else being equal, it's better because you have more physical room for structure. And so if you recall from beam bending type analysis, you're going to get a bigger moment of inertia if you can have a spar that is thicker. So for the exact same amount of material, you can overall get a stronger and stiffer wing. That doesn't mean that thickness in and of itself is necessarily the best thing in the world. There's this AH94W301. It's a 30% thick airfoil, which is great. You think, oh, I got tons of structure. And it's actually not that bad aerodynamically either. But it is a very goofy looking airfoil. We've actually used it in airplanes for particular contexts. I'm not encouraging you, but it is possible to do things that are goofily thick. You got to be careful using airfoils that are too thin, because those can become impossible to build, and it also takes away all of your thickness, right? So there's many something that's used very commonly for model aircraft is a Clark Y, and that's because it has a nearly flat bottom. So if you were building this on a table, that's very convenient if you have a bunch of balsa ribs and you have push pins on a little pegboard. That's a common airfoil. It's not necessarily the most efficient, so I'm not encouraging you to use that. Those are just some airfoils. One we've used many times, some of these Selig-Donovan airfoils are pretty good in terms of getting a reasonable amount of thickness. So that's one parameter. We care about the aerodynamic efficiency as well. In particular, if we know our cruise conditions or loiter conditions, where we're going to spend most of our time, we would like to have minimum drag in that condition. So if we say we're cruising at a CL of 0.5, we can go through and look at a condition of 0.5 and see what the drag looks like and try and pick the airfoil that gets the best drag. Now you have to balance that on the thickness, because less thickness is going to make it look better from a drag standpoint. And you also have to balance that relative to the max lift coefficient. So if we care only about max lift coefficient, then there are things like this Selig S1223. And it is a ridiculously cambered airfoil. The problem with this is that at zero angle of attack, you have a lift coefficient of 1. So if you want to fly at a lift coefficient less than 1, you start going at negative angles of attack, and you're getting separated flow on the lower surface. And John mentioned that briefly. So also, this is nearly impossible to build if you look at this trailing edge. That's extremely difficult. So those are things that you have to balance. In terms of what's happening for the airfoil analysis, that's all very, the XFLR5 is ultimately using Xfoil, and you can go through and find Xfoil. If you just search Xfoil directly, you can find it to download. And you can find different versions. There's different versions that are built for Mac OS as well. And you can go through and download that. There's an Xfoil tutorial that I put together with a bunch of screenshots if you want to use the very old school method that I'm going to demonstrate here. That's on the SharePoint. So let's say we want to look at that, was it E214? I can go through and load, and it's giving me a warning right now that it doesn't think that there's enough panel nodes, which is fine. We can go through and use this command pane to basically resample the number of points that we have in order to get a better distribution of points. So instead of just 61 points, the default with pane is just 160. So you don't have to memorize any of these commands. Step by step, everything that I'm going to show here is in that Xfoil tutorial. And most of it is unnecessary anyway if you're using something like XFLR5 to automate the airfoil analysis. And you'll see this is a very clunky interface in terms of I have to type stuff in manually, but I can do it very quickly if I know what I'm doing. If you don't, then sometimes it's easier to use a GUI. If you know exactly what you're doing, it's not actually that bad. So if I want to modify my airfoil, I can do that in Xfoil, and that's going to be happening in this GDES, or the Geometry Design menu. Go through, hit a question mark, and see some of the commands. So I have this Epler 214. It's got a thickness of 11.1%. Camber is 4%, right? So it's a reasonable camber. I've got a trailing edge, or leading edge radius, and a trailing edge angle. If you have a low leading edge radius, what can happen is stall can occur very suddenly from the nose of your airfoil. And that goes to when you're building them as well. When you physically have your built wing, and if you're looking at it from a 2D type of viewpoint, like what does my wing look like? If it is coming to a sharp point in the nose, your stall characteristics will be terrible. So you have to consider how these are going to be built as well. So I have this airfoil. Let's say I wanted to modify it. Like, 11%, I want to make it thicker. I can use tset as a command and directly input, let's say 14%. And right now, the camber is 4%. Let's say I wanted to make it 2%. I can directly input those. And on this side, you can see the new airfoil is this purple. It's a thicker, less cambered version. Right, so up here, I can see where the camber line is and where it was and what the thickness distribution looks like if it was an uncambered airfoil. Right, so if I wanted to save this, I can. I can go through, hit X. If I hit Enter, I go back to the main menu. I can repanel, and then I think it's save. It may be psave. It's just save. Save, this is going to be E214 mod.dat. And if I go, I will have created a new .dat file that includes many more points. There's 160 points instead of the original 61. And this is the airfoil that I modified. I've changed the thickness. Right, now this header is incorrect, and I really ought to change it. It's 14% thick, and it's modified. So you can keep track of those. Right, so you can go through and make modifications to an airfoil. If you find an airfoil and you like it, but you think, I can't quite fit the spar that I want to make it a little thicker. You can go through and do that very easily. Right, so that wasn't doing any actual analysis. In order to do analysis, we have to go to what's called the OPER menu, the operating point menu. In this case, this is going to be an inviscid analysis, and I can go through and set the angle of attack to 0, and we're getting an inviscid analysis where there is no viscosity, which is not true, but it's at least giving us a starting point. See, 0 angle of attack, getting now CL of 0.35. Right, I can turn viscosity on. Now I need to enter a Reynolds number and a Mach number. So let's say 200,000, Mach number is set to 0. Right now, our drag, technically due to rounding error of the integration, is negative. Right, so in the world in which there's no friction, including numerical error, this airfoil is generating thrust, which is absurd. But that's because we didn't account for viscosity. So I can go through alpha 0, and now I have the dashed line is the same as the inviscid flow result, and I have a yellow line for the upper surface viscous flow solution, and this, what am I going to, I don't know, whatever the not yellow line, teal, I don't know what to describe, light blue. The not yellow line is the lower surface, and you can see that reflected here. There's this little bubble forming as just a little laminar separation bubble. It's a little increase in drag, but it's not a serious concern. And our CL went from 0.35 down to 0.28. Right, so included viscosity. Suddenly our lift is actually getting decreased, and our drag went from being slightly negative to 0.01. Right, so there's a significant difference. So that was just a point at a single angle of attack. Let me see if I remember. One command yater. So I'm going to change that so that I can go through and do a sequence of angles of attack. And this is stuff that John did in XLR5. But we're going to go from 0 to 15 degrees by 1 and go through and execute those results. All right, that's all happening in XLR5, but we can see the results here. And I can go through and I can save those to a file and export them. From this type of analysis, you can get, for the particular airfoil that I'm looking at, what is my CL max. And that's a section CL max, which is not the same as the vehicle CL max. Right, and it's going to be Reynolds number dependent as well. If you don't look at the Reynolds number, you're going to have a problem. Right, so very, very Reynolds number dependent and particular to the vehicle that we're looking at. Right, so I can get these results. Right, that's nice. We can do that with XLR5 again very easily in an automated way. So this is just the more awkward manual way in terms of this interface. So things that you're looking for your airfoil. Thickness, CL max, which you need to calculate based on your Reynolds number. What is my leading edge radius, because that can impact my stall characteristics. Does the airfoil look like it's manufacturable? If you have a very thin trailing edge, can you build the airfoil as it's shown, or do I need to modify that when I actually build it? And things like, if I'm going to fly at a CL of 0.5, then it'd be about 2 degrees angle of attack, and I can look at what my drag is there. I can look at an L over D, for instance, or just a drag directly and try and pick an airfoil that maximizes that aerodynamic efficiency. So this is not a 1D selection for airfoil. There's multiple things that you have to balance. There's literally, 1,500 different results that were at the UAC coordinate database. I think you can't possibly look at all of them, so you're going to have to pick some subset, analyze those, and then pick from amongst them. So as long as your airfoil is not completely inappropriate, the airplane will fly and it will work, and you're not going to be overly penalized. So one of the things that I don't encourage you to do is to spend a month trying to find the best airfoil. You want to find an airfoil that works and that is good enough, but without spending an inordinate amount of time selecting it and doing analysis. So at least getting a starting point is very important. And there's a lot more stuff that we can do in Expo that's in that, or in the Expo tutorial. But most of this functionality is duplicative with the XFLR5 functionality. And in many ways, you can automate the creation of this type of information there easier than you can do it by hand here, which I still use that. But maybe if I can get it to quit here. All right, so that was just exposure to some of the exfoil capability in terms of what sort of airfoils to select. So I'm not going to have a whole lot of time. There's also this aerodynamics and stability material that was posted on SharePoint, and that's just a little primer to try and give you some ideas in terms of the stability derivatives, some rules of thumb, what's happening in a vortex lattice tool in terms of we're taking any sort of lifting surface and dividing it up into a bunch of little quadrilateral elements. Each of those has a horseshoe vortex attached to it. The horseshoe vortex extends to infinity and comes from infinity, has a constant strength, and is bound to the vehicle. And then we define a control point inside our quadrilateral element, typically 3/4 of its local chord. And then we're ensuring that there's no flow through this particular surface. So depending on what our camber distribution or camber line looks like, we can define a normal to the camber surface, and the velocity normal to the camber surface should be 0, right? Based on the induced velocity due to every single little horseshoe vortex that we have on however many lifting surfaces we have, in addition to the free stream flight condition. So that's what's happening in the background. You don't necessarily need to know that, but there are particular limitations. Vortex lattice, our method here, our lifting surface method, is not accounting for viscous effects. So XFLR5, when you use the wing analysis, is doing that. It's integrating some of the drag elements there, but it's not accounting for things like stall. So if I go through and I do a vortex lattice and I tell it an angle of attack of 45 degrees, I will get an answer. That answer will be garbage, but I will get an answer. So you have to be careful in terms of what kind of inputs you're putting in, what type of, so the user itself needs to know what they're doing for that. So that's a particular limitation. Right? We're not accounting for the thickness. So there are thickness effects that can be important, and we're not accounting for those. Things like the fuselage are something that we can accommodate in only very approximate ways. So fortunately, it doesn't impact our actual lift or the stability very much if you have a small fuselage. But those are some limitations here. And then in terms of the rest of this, there's a bunch of slides that they're going through. Some definition, some of this is duplicative to the stuff that Java had talked about. But I go through and talk about what are each of the contributions to all of the stability derivatives, or the most important stability derivatives physically on the aircraft. Right? So in terms of C and beta is what we're going to use to determine how big our vertical tail needs to be. So the vertical tail sees some increase in its local angle of attack based on an increase in side slip, and we need to point the nose toward the wind. And so C and beta is often called weathercock stability. Right, so we're going to use this in particular. And there's a range of other ones going through. Talking about the effect of trim, we'll go through and do that in terms of the demonstration. But what happens is, depending on how stable your aircraft is, it actually changes our performance. Right? So we go through and look at a lift curve. Once you include trim, depending on how stable you are, you get a reduction in your lift curve slope. We also get a reduction in CO max, all right, for stability. If you're too stable, you're actually developing less lift, and you're less CL max, less lift curve slope, and you can eventually start to over-stress your elevator. And so here at 20% static margin, at 15 degrees angle of attack, we need a trim elevator deflection of almost 30 degrees. And that's probably too much. Probably physically can't do that without the control surface failing. So once again, this method can give you what kind of elevator deflections are required for a given condition, but if it goes through and it solves and your elevator deflection is 80 degrees, that's wrong, right? There's going to be some sort of separation that occurs well before that, right? So you need to limit things. So there's particular physical limitations that you need to keep in mind as a user when you're operating these tools. So these rules of thumb here are basically just the same as what I talked about in the design guidelines that was shown a month ago or a while ago. I don't remember exactly how far. So some of these are guidelines, and we're going to discuss why they are the way that they are, what sort of values, and how we can calculate those. Right? So important to keep in mind here that as the user, you have to bring some knowledge to the table. You can't assume that these tools are going to tell you when you're doing something wrong. You need to know what it is that you're doing. Right, so there are multiple methods to do this kind of analysis, and in terms of the XFLR5, right, is doing a lot of the same things, or can do many of the same things, but there are particular things that AVL is going to do significantly better, and I encourage you to use that in terms of looking at your stability and the sizing, and we'll go through the particular analysis. If you want to find AVL, if you just search, even AVL wing is going to show up, and that's coming from the same professor at MIT who put together XFoil, and it's another tool that works pretty much the same way. You can find executable versions here, again, for Windows, as well as older one for Mac if you have that. There's some documentation here, and it's okay, but I also put together the AVL tutorial, which has, again, a step-by-step with screenshots of typical commands, what it is that you're doing and what it is that you're looking for. So you can go through and download that. Also on the SharePoint, there's the Windows version is already on there. We've got an interface, and we'll talk about that eventually, but we're not going to start with that. It assumes that you know some things. To define an input file for AVL, we have to define some reference parameters. You have to define what is my reference area, chord, and span. That's going to be based on your wing. The units don't matter. This is all set up for inches and square inches. You can set up in meters and millimeters or furlongs or whatever. Whatever the units are, the calculations are going to work the same way. You just have to make sure that you're internally consistent. We also have to define a reference point. The reference point is to calculate moments. And so you go through and you calculate a pitching moment. In order to calculate a pitching moment, they have to have every reference point. A reference point is defined here in three-dimensional space in terms of X, Y, Z. In terms of the stability of your aircraft, that reference point is your center of gravity location. Now, just because I set my reference point here at 1200 does not mean when I build the aircraft that my center of gravity will be at 1200. It's just telling me if the analysis works out for this particular reference point, then I need to make my center of gravity 1200 or close to it. In order to define our lifting surfaces, we're defining them one by one. We go through, we have a wing, there's a tail, there's a vertical tail. Those all exist. For each of those, we have to define, first of all, how many chord-wise cuts. Right, so 10. Use 10. That's in the AVL tutorial as well. This is the number of span-wise cuts. We're defining how many quadrilateral elements. This can be increased or decreased. There is a limit in terms of how many you can include in AVL, but I don't think people typically run into it. What can happen if you put too many elements, you get too small, each element becomes too small, and the numerical error, just due to rounding of a double, can start to add up to be significant. For each of our lifting surfaces, they're defined into a series of sections. For each section, we have to define the leading edge or the starting point of that section in X, Y, Z. Right? So this starts 2.5 inches in front of the nose, and then it's 0, 0. Then we define what the chord is. The chord is 22.5 inches. We define a local twist angle. Right? That could be an incidence angle, but that's what AINC is referring to. And we can define the number of span-wise cuts per section, or in this case, we include the overall. You won't have to mess with that directly. We also have to define what is the airfoil at that section. If I define this section and then the next section, and I put different airfoils, it will be linearly interpolated between them. So here I can directly take an airfoil file, in this case the SD7062.dat, but we could use our E214 or E214 mod. Right? Or I can define a NACA. I go through, say, NACA 4412 and replace that. So that defines one point, and then I have to define the next point, and I've defined one section. It's 4.5 inches wide. We started a Y of 0. We finished a Y of 4.5. It's a constant chord of 22.5, and it has the same airfoil. And I go through and I have a tapered section. I have X, Y, Z. So in this case, this is swept. There's no dihedral because Z is still 0. And the chord is down to 10 inches. All right, so we have an airfoil file, and we define a control surface. In this case, there's two control surfaces. They're on top of each other. All right, so this is modeling a flaperon. And we have ailerons that can also be deflected like flaps. And you would sum up your aileron deflection and your flap deflection. The hinge location is this number right here, and that's going to define the hinge location is 0.7 down the chord. Right, so the last 30% of this section of my wing is control surface. And then there's a final section that goes out to the tip, and it also defines the end of that control surface. So I have a control surface that goes over this longer section. Right, the horizontal tail and vertical tail are defined in the same way. Right, so this is just introducing you to this. You don't have to use the text file directly. And we have another tool that you can use that will help you visualize as opposed to this being extremely abstract. Like here we have a bunch of numbers, you're looking at it, and I'm talking about things, and it's probably going right over your head. And that's perfectly fine because we have other tools to look at. So if I want to get a visualization of the results, I can do that. But for now, we're just going to actually run it, and then we'll talk more about creating things with this interface. All right, so that's my input file. I have it all defined. I know in this case it works, right? But ultimately we're going to have to find for our particular aircraft what works. When I open this, this looks just like that X-foil. Right? We've got this nice DOS interface. We can type some numbers in, or letters and numbers, and create some commands. So the first thing I need to do is to open that file. Went through and open. Sometimes if there's a problem with your file and you try and open it and it immediately closes, that means that there's a problem with your input file. So now I can go to the open menu and I can get a look at what the geometry looks like. Right? So we talked about, we had a point here that's 2.5 inches in front of the nose. This is the actual nose of the 0 point. It goes across 4.5 inches and then goes back a little swept section and then goes all the way to the tip at a constant 10 inches. Right? Those are the different sections that we defined. Right? And the tail was defined in the same way. Right? So this, with a blended wing body here, there's no actual fuselage, so this is extended, so there's a little bit more room to put stuff. Right? So this is a design build fly aircraft from 2009. So it's a very old file that I've used for teaching AVO. Again, to probably, I don't know, maybe as many as 1,000 people at this point. So from here, I can look at a couple things. If I want to, I can see what do my camber lines look like. So these are what are actually used. From your .dat file, it's not looking at the thickness. It's using the thickness to calculate a camber line and then using the camber line for the physical calculations. And so this camber line is defining all of our no flow through the surface conditions, and I can go through and see, does my camber line look correct? Well, these are flat plates, right? So they are essentially on top of each other. This has some positive camber. That's what I would expect. I can turn that off. I can look at the normal vector, and this is the normal to the camber line vector, where that is defining the no flow through the surface condition in order to solve the strengths of all of my vortices simultaneously in order to get a closed solution. All right, so I can at least, again, visualize this is basically just the camber line, only now the normals to it. All right, there's many other things you can do here in terms of changing the angles, etc., but it's very awkward because it's a DOS interface. So you can play around with those if you want to, but this gives you a starting point. Does this look like what I wanted it to? Right, maybe I started with a VSP model and I can go through and compare. In this case, it's not the same, but you can go through and see, does it look the way that I think it should look? And so now I have to define the actual operating point in order to run an analysis. Right now, the angle of attack is 0, the side slip is 0, the roll rate is 0, etc. All our deflections are 0. If I want to execute, I can just hit X. It's going to go through, solve the strengths of all those vortices simultaneously, get a result. So the result is at 0 angle of attack, we have a lift coefficient of 0.32. I have an overall drag here estimate that's not including everything. In this case, we're getting some numerical inconsistencies, and it doesn't actually make sense. We have a pitching moment coefficient that's not 0. That means that the airplane is not in trim. If the airplane was actually flying in this condition, it's negative, so the airplane would start to nose over. And if the pilot did nothing, or the control system did nothing, eventually it would nose into the ground and destroy itself. Right, so trim is something that's very important to us. All our control surfaces are 0. I can, instead of controlling angle of attack, I can control lift coefficient. Let's say I want to trim the aircraft at or I want to analyze the aircraft at a lift coefficient of 0.5. I can go through, hit A space C for lift coefficient, and then 0.5. Oops. An extra number. So basically now we're setting the angle of attack such that we have, instead of a fixed angle of attack of 0, it's giving me an angle of attack such that I get a lift coefficient of 0.5. So if I execute here, it's going to solve, and now the angle of attack to get a lift coefficient of 0.5 is 2.06 degrees. So that's nice. Right, so we solved a number there. This far field is still being kind of wonky. I'm not entirely sure why. All right, so we're getting our lift results there. We can look at this Trefet's plane plot that's looking at the far field approximation, and it opens up a distribution like this. So typically I get rid of the perpendicular and the downwash. You can look at those distributions, but these two curves are the ones that I care about the most. So there are two elements here. This is for both our wing and our horizontal tail, which is obviously much smaller because that's normalized with respect to the wing reference area. And we have this dashed line, which is the section lift coefficient. And then we have the section lift coefficient times the local chord divided by the reference chord in this solid green line. So the actual lift being generated across the span is represented by the green line. Right? So we get this bulge in the center body because we have a higher chord. Makes sense. This may not be the most efficient shape, right, in terms of minimizing induced drag. If we look at this section lift coefficient, we can see the overall airplane is at a CL of 0.5, right, which would be right here, but there are portions of it that are above 0.6. Right, so here's the first thing that we can do. If we have our wing, if we've picked an airfoil, and we know, let's say, that the SC7062 at a Reynolds number representative of our vehicle has a max lift coefficient of 1.7. If I get a max lift coefficient, or if I get a section lift coefficient that's above 1.7, I can no longer trust the results. Separation is starting to occur. Right, so let's go through and change the angle of attack to 15 degrees and look at the same results. And we said 1.7, that's right here. This whole region is stalled. Therefore, we can't actually get a CL of 1.57 for my airplane for this particular geometry. I think it's this.
Is that useful for, so I know that it's typically important to understand where the stall begins.
Yes, and we'll talk about that too.
Okay.
So, I mean, I already know the answer is around 12 degrees, so I went ahead and put in the results here. So it's about 12 degrees. We get our max lift coefficient 1.7 is right around here. So if you look at where this is occurring with respect to the span, it's occurring essentially at the little shoulder joints where we have a discontinuity in our geometry. Right, so we get stall, that means stall is occurring here. If there was a big spike out here, that means we would be tending toward tip stall, and that's terrible. Right? You would like to stall toward the inboard. Right? So this just seems like reasonable from a stall characteristic standpoint. But our section CL max was 1.7. Our vehicle CL max is here like 1.35, and a pretty significant reduction. Right? Part of that is the particular geometry that we selected, and we made a compromise by increasing the geometry for the center body, and that's causing some problems. Right? So we can get from our section CL max our vehicle CL max, approximately. Right? This is not an exact result. We're getting a reasonable estimate using information that we already have. That's not trimmed. Trim is important. So if, let's say, we wanted to trim, I can trim by going through and making my elevator, instead of being set to an elevator of 0, I can go through and say, I want my elevator, which is D3, set to give a pitching moment coefficient of 0, and then re-execute the exact same results. So this is at 12.3 degrees, we're at 1.35. Now, instead of 1.35, it's 1.29. All right, so we got a reduction in our lift, and we have an increase in our elevator deflection required. So here it's taking negative 13.7 degrees, which is trailing edge up. So our elevator is trailing edge up when elevator deflection is negative. But our CM here is now 0. And so this is the trimmed CL max, approximately. And again, I can vary this a little bit, but you see that we actually had a reduction in our felt lift. Right, so the CL max is nice. We can go through and trim it. In order to trim it, you also have to define the center of gravity, which we'll get to when we look at the stability results. Right, so this is how we can trim the aircraft. And the rule of thumb that I provide is that at the maximum CL of your vehicle, the elevator deflection should be less than 15 degrees. So this is an optimistic estimate in terms of the effectiveness of our elevator. A physical elevator past around 25 degrees of deflection will start to have the possibility, certainly, of separation occurring and it losing its effectiveness. So this is a little bit conservative here at 15 degrees. And in this case, you can see it qualifies. It's below 15 degrees. Right, so that means this elevator size is reasonable. All right, so I can go through and let's say I wanted to specify my CL directly. Say, okay, I wanted 1.3 degrees. I can do that too. All right, so now the angle of attack is set such that we get a lift coefficient of 1.3, and our elevator is set such that we get a pitching moment of 0. And we have the results here. And maybe this has some level of stall, and maybe we ought to reduce that slightly. Looks like our actual trim CL max is somewhere more like 1.3 instead of 1.7. All right, so we can save these results in different ways. We can get to other results. I'm probably not going to have time to get to everything I want to here. But there's other things we can look at the stability derivatives. So this is a full set of stability derivatives, like is discussed in the aerodynamics and stability slide. So in terms of things like CL alpha, right, CL alpha in terms of per radian is 4.6. CM alpha is negative 0.5. Static margin is defined as the negative of CM alpha divided by CL alpha. Right, so I take the ratio of this parameter and this parameter. Right, so in this case, it's somewhere around 11%. Right, so the negative of this, which means a negative CM alpha, is stable, divided by CL alpha. The ratio is around, it's more than 10%. So it's around a static margin of 11%. Okay, that's good. We have other parameters here. CL beta is our roll stability. It has to be negative. It's a pretty strong function of CL, so you can't give a direct number of what it should be. CN beta is that weathercock stability. So CN beta here is positive 0.075. The primary contributing factor to CN beta is the vertical tail size and location. The bigger it is and the further away it is and the more moment arm it has, the more effective it becomes. Right? And the guidelines for CN beta, in terms of per radian, it should be somewhere between 0.06 and 0.12. And in particular, probably best to be somewhere in the mid-range of that, close to 0.08, 0.09. And so this is a little low, but it's not unreasonable.
Could you very quickly explain why there's an upper and a lower bound rather than...
If your tail's too big, it's a waste.
Okay, thanks.
I mean, you can make your tail enormous, but now it's heavier, and now it's draggier, and now it's actually making your center of gravity harder to achieve. Yeah. Stability, now you want enough, but not too much.
Thanks.
If it's too small, the plane's going to fly poorly. So that's a basic rule of thumb. So this is driving vertical tail sizing. The exact shape in terms of the geometry is to some extent arbitrary. If you want to do tapered and swept and whatever, you can do all that stuff. So we also have the damping derivatives here. So the roll damping derivative is CLP. Pitch damping derivative is CMQ. Yaw damping derivative is CNR. And those are all negative. They all have to be negative, so that's good. I would expect them to be. In terms of all, this is a full set of stability derivatives that in combination with Simone's inertia, you can calculate the dynamic stability characteristics. If you have no idea what I'm talking about, don't worry about it yet. Maybe someone on your team needs to do the analysis, but not everybody. And then there's a set of control derivatives. Nowhere in the documentation does it state this, but all of the control derivatives are in per degree. All the stability derivatives are in per radian. All the control derivatives are in per degree. So keep that in mind if you're trying to use this to build a full simulation model, and you also included the control characteristics. There are control characteristics here, but they're per degree. So that's something to keep in mind. So we also have the direct neutral point in terms of our location. So if we recall, our reference point was at 1200, so x of 12. And the neutral point is behind that. The neutral point has to be behind the center of gravity for your airplane to be stable. So it is, and we see our 10% static margin, and this is consistent with that. There's also this parameter here, the ratio of these stability derivatives as the mode approximation for spiral stability. You can see it needs to be greater than 1 if it's spirally stable. Is this greater than 1? Not even close. If you have an active control system, that doesn't matter that much. So don't worry about trying to make your airplane spirally stable. Unless your pilot falls asleep, you should be okay. Unless your autopilot completely craps out, you should be okay. So all of those can be saved, again, to a text file. So let's say I want to save, stability.out. Oops. And now I have this output file, which is basically just a complete set of that information, which I can read or modify or copy or mess with any way that I want to. All right, so other things that we can do here. We can get hinge moments. Actually, I need to re-execute the analysis. I accidentally backed out. So if you want to look at the hinge moment coefficients for your control surfaces based on these conditions, we have those. Right? So basically for the aileron, the flap, the elevator, and the rudder, what are the hinge moment coefficients? You can go through and get a perceived moment and look at that for servo sizing characteristics. Hinge moment analysis is highly imprecise and depends a lot on the details of your hinge implementation. So take these numbers and increase them by 50% or maybe even just double them. So if you try and size directly for this, you can cause problems. We actually used this to size this once, and it didn't turn out well for the aircraft. They were undersized. So there's a lot of uncertainty to these hinge moment values, but they do give you at least a starting point. We can go through and we can get the strip, shear, and bending moment analysis. Again, I can output this to the screen or I can save it. So if we look across the surface, across the span, what is my shear load and the bending moment? These are again set in coefficients where you have to look at whatever units you've normalized them by in order to get the loads, and these can be used to perform structural analysis. Let me see, we got other, well, those are the main parameters, and you can go through and save a lot of different stuff, right? So there's a lot of things that we can do here. We get CO max, we can get our center of gravity location, right? Not necessarily where it is on the aircraft, but where it needs to be to make the airplane have a sufficient level of stability. We can figure out where our tail needs to be and how big the elevator needs to be in order to trim the aircraft. How big does our vertical tail need to be in order to get a sufficient level of C and beta. And that's giving us the basic tail size and stability characteristics of our plane. And so this is all the command line version. I also had a student who a couple years ago put together an interface, and it is on GitHub. If you search for AVL interface, you can find it. I provided a link to the executable already. But if you wanted to mess with it, you're more than welcome to. It's open source. And it's just a C# implementation that goes through and automates some of the AVL stuff. Particular, the advantage is that instead of defining a text file and going through and typing a few numbers, we can see what it is that we're doing. So if we open it, we get this GUI interface. One of the first things we have to do is select the location of our AVL executable. And so wherever it is, we have to find it and tell the tool where that is so that it can run it. Right? And it can run things, uses some parallel computing, etc. I can create a new file, or I can just open this buzzed final. And so the same way that we went through and defined our wing, and we look surface location, I can change my chords. I can change the X location, the Y location, the Z location. I can change what the airfoil is by selecting a different file. Excuse me. Change the airfoil, select a different file, etc. I can go through and change the control surface. All right, so in this case, the elevator is defined here. I can change the name, or I can delete it. I can deflect. I can change instead of 30% chord, and you see a little bit of a visualization here in terms of the darkness. I can make it 50% chord, and now I have a bigger elevator. There's diminishing returns to making it bigger. Really, there's no reason to go above 50%, and you don't want to go too small either. So I can change the characteristics here. I can change the section. Like this is a 7-inch chord. I can go through. I can make it 8. So that's one section, and then go through the other section, and now it's bigger. I can change this chord. It's 22 inches, right, relative to here. I can go through and make it 15. You can see that has updated the geometry, and I can go section by section and change those. All right, so this is change the shape, and I can see how I modified things. I can save the file, save as a new one. One of the things that we can also do is set our reference parameters based on this particular surface. So instead of I had to go through and calculate these, I can just hit this button, and now I got new reference parameters. It's still 104-inch wingspan, but the reference chord and the reference span has changed. And if I change it back, I can again reset those, and it goes back to essentially what it started as. I can change the XCG. Instead of 12, I can change what it is here and go through and rerun it. This CDP, if I have an estimate of my parasitic drag coefficient, which I can get from this analysis in VSP, I could just plug that in here, and that's going to get added to all of my drag numbers. So I include both parasitic and induced drag. Not necessarily perfect results, but we'll get something out of that. And so this is definitely valuable in terms of creating a file and making sure that it's formatted properly, because the program is not very forgiving if you make one little mistake in terms of you have an extra character or you forget something. It just doesn't work. So if you go through this tool, it will at least definitely work. So I can go through and run stuff the same way that I ran things before. Let's go through a series of angles of attack, 0 to 15. I can just accept, create those run cases, and it's going to go through and run all of them. And so 15 may have been too many. That's fine. So the same kind of commands that we did before inside of the AVL text command line interface. We can do a lot of those here. This is just a sweep of angles of attack. For each of those, I could go through and run and set it to trim the aircraft the same way that we did before. But it's going to take a little bit longer to do that, and then we'll get a little bit of a visualization of the results here. Right here we have CL versus alpha, and this is a CL versus CD curve. And there's some other graphs. The graphing is the thing that does not work particularly well. This is a fairly limited tool. There are certain things that work very well in terms of creating files and running stuff, but the graphing leaves some things to be desired. So you can go through and mess with some of the graphing elements. And we can go through and we can look at any individual one here. And here we have the Trepid's plane type plot. You can see 2 degrees versus 15 degrees. What does that look like? What are the values across here? I can look at individual cases. And for this, I can look at, let's say, 0 angle of attack. I can show all of the raw data. Right? So this is a massive data dump. I can go through and copy that. I can export it, save it. I could look at just the total forces. And so this is going to be the lift, drag, etc. I can look at the raw stability. So this is the view of all the stability derivatives. And that's here. And so all of these I can go through and query any of those and save anything that I'm interested in. Right. Another thing that I can do is if I like that command line interface, I can still do it here. If I go through and I want to run an analysis at the lift coefficient of 1, I can do that. It will run. And and I have results. And so this is just a same type of command line where we've created an instance of AVL that we can run. So that was not necessarily at the speed I wanted to cover all of this stuff, but the basic idea here is that there are a number of questions that we have to answer for our aircraft. All right. We have our requirements. We should have a configuration, a basic idea of the size. Now we need to figure out what's the aerodynamic shape. Where will all the components be? What's my airfoil? Where does my center of gravity need to be? How big does my tail need to be? And how stable is my aircraft? How big does my elevator need to be? How does my vertical tail need to be? All of those can be answered with AVL. Now, some of those you need to, looking at CLMax, for instance, you need some airfoil results for. Right? So you need to run Xfoil or XFLR5 for that. And we have some rules of thumb here in terms of how to get started and run things. And I'm available for questions. Again, I've taught many students to use this and design many different aircraft using AVL. You can go through and change our views if you want to look at it. Front doesn't look very interesting when everything's flat plates, but top, right, it may be useful for top when you're defining things. So I encourage you to open the tools, play with things. We've provided a number of resources here. This input file is provided to you. You can go through and mess with that, along with the airfoil. Get the executable for AVL and the AVL interface, and make sure that you link those the first time that you run it in terms of where is the executable. And you should be able to run those, query them, see what it looks like. You can go through and you can create a new one, like let me create just a test file here. And there's a dummy file that includes only a wing and tail with just Hershey bar, taper ratio 1 type construction. But I could create a new, and add a new surface. I call that the vertical tail. And now it's in a silly location, right? But I can move it back to wherever this one is. It's 30. And then the Y is going to start at 0, and then let's say we make it now we've got a vertical tail. And I can go through and mess with. The chords in this case are too big. Now I've created a new section, right? Added a new vertical tail. I can go through and now save the results. I can reopen this and run stuff. And do the other things that we were mentioning in terms of setting the reference parameters, messing with the CG location, ensuring the airplane is stable. So whenever you start, the first thing that you can do is figure out, this is my geometry. Does it look the way that it should look? Look at the untrimmed results. Figure out where my center of gravity needs to be to get my static margin at an appropriate location, and then start looking at trim. Right? Don't look at trim first. Look at trim after you've figured out where the center of gravity needs to be for the correct level of static margin. So I know that was extremely quick and that there really isn't time for questions at this point, but don't hesitate to ask questions in the future. Send me an email. If you send me a file, I can often figure out if there's a particular problem with it or what's going on. And again, if you create stuff with this interface, it should be formatted properly where it actually runs and works. So is there anybody still there to ask questions, or did I go too far over?
I was just going to add, Carl, and I have recorded all this, so it'll be posted probably by Monday, so students could watch again.
There is one other website that we find useful. It's called Airfoil Tools. And what Airfoil Tools does, it's got most of the percentage of the Selig airfoils, but it has Xfoil calculations for all of them. So it's a good way to get a survey of the type of airfoils you might want to look at. After you look at that, you're going to have to go and run Xfoil and some sort of a wing analysis to go with it. But it's a good way to look at an awful lot of calculations quickly.
I don't know, at least here at Tech, and I think there's one other school has fall break on Monday. We will still be having a lecture. Expect people to still call into that, even if you're on break. At the very least, you can review the recordings afterwards.
Can you send out the link for that? Again, the same one as you sent
It's the
out.
same, the lecture is the same, should be the same.
Okay.
If it isn't, email me and I'll send it back.
Awesome. Well, thanks for your tutorials this morning, Dr. Sullivan and Carl. We appreciate it, and we will see everybody Monday morning.